Hello friends, welcome to the today's session. Today we will be discussing the liquid flows inside a container, and these two types of flows are there. The flows are nothing but the steady flow, which is also called as a streamline flow, and the second type of flow is called as the turbulent flow. So let us start with the first topic, that is nothing but the steady flow. Friends, in everyday life we are using so many examples of the streamline flow. For example, inside a pipe water is flowing. Inside a pipe water is flowing, and if the velocity of the water which is flowing inside the tube is very small, then water will flow like this. The water will flow like this. Okay. Suppose there are 2 points. If I consider, let us say this is one point, let us say this is point A, okay, and let us say there is another point, let us say B over here. Now what happens in this case is that if the liquid is entering at a point A, then the flow of liquid at a point A is such that if one molecule is going from this point, suppose this is the molecule which has gone from this point A initially. Now the velocity of this particle and the path which this particle has followed at point A, the same its predecessor particle, it will also have the same path and the same velocity or same speed. Okay, such a kind of ordered flow of the liquid, that is called as a streamline flow. So first of all, we will note down the definition of streamline flow, and then we will discuss in the more detail. Okay, so the flow of liquid is called steady flow or streamline flow if each particle of the liquid passing through a given point, passing through a given point has same path and same speed as its predecessor. Okay, so this is nothing but the streamline flow or steady flow. Okay, now see, the flow of liquid is called steady flow or streamline flow if each particle of the liquid passing through a given point, let us say this is the point through which the liquid molecules or particles are passing. So if the liquid molecule, for example, initially this molecule has passed through the point A, then whatever the path this molecule had when it was at this point, or this particle when it was at this point A, then both the particles when they were at the point A, it will have same path as well as same speed. Okay, such a kind of flow, it is called as the streamline flow, or it is called as the steady flow. Okay, so in other words you can say is that steady flow or streamline flow, that is a ordered flow of the liquid. Okay, and the condition for this kind of flow is that it has the liquid has to move with a very small velocity, then and then this you will get a streamline flow or steady flow. Now next type of flow it is there, that is called as the turbulent flow. Now what happens, suppose if the liquid is pushed inside a tube at a very rapid rate. So what happens if a liquid is pressed inside a tube at a very rapid rate? Then what will happen? Such a kind of disciplined flow of the liquid, it gets disturbed and liquid becomes disordered. And such a kind of disordered flow of the liquid, it is called as the turbulent flow. Okay, so if the liquid in a tube is pushed at a rapid rate, is pushed at a rapid rate, the disciplined flow of liquid, becomes disordered. Okay, disordered. Such a kind of flow is called turbulent flow. Such a kind of flow is called turbulent flow. Okay, so you can note it down one thing over here, that a turbulent flow, it is a kind of disordered flow. Okay, and see, in steady flow we have assumed that the liquid was traveling with a very small velocity. Here in this case, what we are assuming is that liquid is not traveling with a small velocity, because liquid is pushed inside a tube at a very rapid rate. So from this observation, you can decide that it is the velocity of the liquid which decides whether the flow will flow in a steady way or streamlined way or in turbulent way. Okay, so it is the velocity with which it is moving. Okay, so that velocity, it has a special name, that is called as the critical velocity. Before that, what we will do, we will just see the schematic of the turbulent flow. Okay, so turbulent flow schematic, it is like this. For example, the molecules in a turbulent flow, it will move in a random fashion. Okay, so due to that one, eddy currents may be developed in case of turbulent flow. Okay, so that we have to remember. So this is a schematic for a turbulent flow, this is a schematic for a steady flow. Now what we were discussing is that steady flow and turbulent flow, they are classified based on the velocity of the liquid with which they are flowing. Okay, so that velocity, it is nothing but, it is called as the critical velocity. That is called as critical velocity. Okay, now what is this critical velocity? When the velocity of the liquid becomes greater than the critical velocity, steady flow of the liquid becomes turbulent flow. Such a kind of velocity, it is called as the critical velocity. So we can consider here the velocity at which the velocity at which steady bracket, so streamline flow of liquid becomes turbulent flow is called critical velocity. Okay, so it is the velocity of the liquid through which the liquid is flowing, and when this steady flow or streamline flow, it's get converted into the turbulent flow, that value of the velocity, that is called as the critical velocity, and this critical velocity is denoted by the symbol Vc. Okay, so in the next topic we will be seeing now how this critical velocity for a given liquid it can be calculated. It was the scientist Reynolds who had given his experimental outcomes in the form of one relation. That relation we will be deriving now, and we will verify that relation by using the dimension analysis. Okay, so let us start with the new topic. Our next topic, that is nothing but the Reynolds number. Okay, Reynolds number. Reynolds number. Okay, now what is this Reynolds number? Is that Reynolds have performed series of experiments on the flow of the liquid, and he proposed that velocity of liquid at which the steady or streamline flow of the liquid it gets converted into the turbulent flow, that value of the velocity, that is called as the critical velocity. If the velocity of the liquid becomes greater than the critical velocity, streamline flow, it is converted into a turbulent flow. Based on the experimental details of the Reynolds, he proposed one mathematical expression for the critical velocity of the liquid, and that expression for the critical velocity of the liquid, it is given by Vc is equal to R eta upon rho d. Okay, here in this expression, this quantity R, this is called as Reynolds number. This quantity, that is called as Reynolds number. The quantity eta, that is called as coefficient of viscosity. This number, that is called as coefficient of viscosity. This number, it is called as coefficient of viscosity. The next symbol, that is rho, that is called as the density of the liquid. Density of liquid. And the parameter d, it is nothing but the diameter of the tube through which the liquid is flowing. Diameter of tube through which this liquid is flowing. Okay, so now what we will do now, we will try to verify this expression by use of dimension analysis. Based on the experimental results, what Reynolds have proposed is that this critical velocity of a liquid at which turbulence is set, it depends upon the three parameters. He proposed that this critical velocity, it depends upon the coefficient of the viscosity, it depends upon the density of the liquid, and it depends upon the diameter of the tube. From this expression, from his statements, according to Reynolds, Vc is directly proportional to eta and rho and d. Okay, A is the dimensional coefficient of eta, B is the dimensional coefficient of rho, and C is the dimensional coefficient of d. Okay, now if I remove this proportionality sign, I will get Vc is equal to R into eta raised to A, rho raised to B, and d raised to C. Here we can write, here A, B and C are dimensional coefficients. Okay. Now taking the dimensions of the both sides. Taking dimensions on both sides. Okay. Now see, Vc, it is the critical velocity, so its unit is meters per second. So I'll write its dimension m, l and t. So as it is a meters per second, so it is meter for length L1, and per second, so it is -1. T is -1. R is a proportionality constant which is a dimensionless number, so we will not bother about the R. Okay, next quantity it is eta. Eta it is nothing but the coefficient of viscosity. We have derived its dimensions in our earlier lecture, which is nothing but m1 L minus 1 T minus 1. Okay, next quantity it is there, that is the rho. That is nothing but the density of the liquid. So this density of the liquid has the formula mass upon volume. So mass is measured in terms of kilograms, so it is L1. Volume is measured in terms of meter cube, so it is L3, but it is per meter cube, so it is L minus 3, T raised to 0. And the next quantity it is D, which is the diameter of the tube, so which is a length scale. So we will write it over here, M0, L1 and T0. Okay. Now for these quantities, the dimensional coefficients are A, B and C. Now we just have to apply the simple laws of indices, which is nothing but M raised to A, L raised to minus A, T raised to minus A. So this is for the first bracket. Similarly, we will simplify the second bracket, M raised to B, L raised to minus 3B and T raised to 0. That is for the second bracket. For the third bracket, we can write M raised to 0, L raised to C and T raised to 0. Now further, the right hand side, left hand side, it will be same. This is equal to, now we will just simply take M to the power in one bracket and L to the power in another bracket. So it is M to the power, here it is A, here it is B. So M plus A plus B, and here it is 0. So don't bother about this. L raised to, here it is minus A, it is minus 3B, and it is C over here. So it is minus A minus 3B plus C. And T raised to, in this case, minus A 0 0. So it is minus A. So this is equal to M raised to 0, L raised to 1 and T raised to minus 1. Okay. Now, equating the coefficients, powers of the indices, if I equate this, I will get the first equation, that is A plus B is equal to 0. Similarly, if I equate the powers of L, which is 1 on this side and this, minus A minus 3B plus C on this side, this is equal to 1. And I'll get the third equation, which is minus A is equal to minus 1, which is nothing but the power of T. Okay, so from this equation we can directly write A is equal to 1. So this is the first dimensional coefficients. So we got the value of A to be 1. If I substitute value of A in this equation, if I substitute this value of A in this equation, what I'll get? A plus B is equal to 0. From this equation, I can write B is equal to minus A. Therefore, B is equal to minus A. Value of A, it is 1. So it is minus 1. So B is equal to minus 1. That is the second coefficient. Now we will substitute value of A, B in this equation, which is therefore minus A minus 3B plus C is equal to 1. Is equal to 1. In this we will substitute A equal to 1 and B equal to minus 1. So A equal to 1, so it is minus 1. B equal to minus 1. Minus 1 into minus 3, that is plus 3. Plus C is equal to 1. Okay. 3 minus 1, it will becomes 2 plus C is equal to 1. So if I consider C is equal to, it will be 1. This 2 is plus on this side. If I transfer on that side, it will becomes minus 2. Therefore, C is equal to minus 1. So I get the first value, the last value, that is C equal to minus 1. So I got A, value of A, value of B and value of C. Now what I do, I will substitute this value in this equation. Okay, let us call this as an equation 1. Substituting A equal to 1, B equal to minus 1 and C equal to minus 1 in equation number 1. In equation number 1, we will get VC is equal to Vc is equal to, so it is R eta raised to A. Value of A is 1, so it is eta raised to 1. Rho raised to B, so B value of B it is minus 1, and next one is D raised to C, value of D it is minus 1. So if I rewrite this, I can rewrite this in this fashion, R raised to eta upon rho D. Okay, so finally we will get an expression for this in this fashion. We can write Vc is equal to R into eta divided by rho D. Okay, so this is the formula for the critical velocity which is given by the Reynolds. Okay, where R is called as the Reynolds number. From this one you can get a rough idea for the steady flow or turbulent flow. If your coefficient of viscosity, which is rho, which is eta, has very high value, then density of the liquid which has very low value, and diameter of the tube through which that liquid is flowing, if it is having a very small height value, then this value, if you substitute this value in this expression, your critical velocity, it will be very high. Okay, the value of the critical velocity, it will come out to be very high. In such a kind of scenario, your liquid will prefer to have a turbulent flow. In order to have a steady flow, your coefficient of viscosity of the liquid has to be a very small number, your density of the liquid has to be a very high number, and also a diameter tube whose diameter through which the liquid is flowing, that diameter also has to be a very high number. Then your critical velocity or the velocity of the liquid through which it is flowing, then it will come out to be a very small number. In such a case, your flow will be streamline flow. Okay, and in this case it is a turbulent flow. So you have to remember this thing. Okay, so that these numbers are given by the Reynolds number. Okay, and it is related to this way. I hope you people have understood it. Okay, we'll stop here for this lecture. We will see the next topic in our next